Hi, we are the wastewater experts, and today we are presenting on the modeling and optimization of the Northwest Advanced Wastewater Treatment Plant. Northwest Advanced Wastewater Treatment Plant works using a 5-step biological process. The process consists of a series of basins. As wastewater flows through the plant, it encounters 5 basins, one for each step. The plant is rated to treat 10 million gallons a day of wastewater and is currently undergoing an expansion, which is set to be finished later this year. After the expansion, the new plant should be able to handle 30 million gallons a day of influent. The focus of this project is to analyze the current rating and optimize the process under the current plant equipment specifications. This will be done to attempt to increase the quality of the effluent, reduce the operation cost, and reduce the environmental impact. The expansion will act as a scaled-up version of the current plant, meaning the results and optimization will still be applicable once the expansion is finished. The approach for the optimization of this process will be to model the advanced wastewater treatment plant using BioIN. For the simulation, effluent volumetric flow rates from January 2016 and max reported concentration data from the Northwest plant is specified in this model. The simulation output using the plant specifications will be compared to the reported effluent concentrations in the Northwest report, and then we will optimize the model and compare to our initial model. In order to optimize, we will then be manipulating the power of the aeration basins and the amount of sludge being recycled in order to find optimum effluent concentrations.
The block diagram shows the basic overall setup of how the Northwest plant operates. The incoming raw sewage first enters the headworks to remove large debris and majority of the solids that are in the influent. The water then starts the 5-step biological process by entering the fermentation basin. It then goes through 2 sets of anoxic basins and 2 sets of aeration basins. The bacteria in the water goes through a period of stress. This is done by changing the environmental conditions. This makes them consume more phosphorus and nitrogen. Once this is done, the water is sent to secondary clarifiers to remove and collect the activated sludge. The water then gets processed by going through the filters, chlorine contact chambers, and possibly deacidification and dechlorination. The extent of the remaining steps depends on where the processed water is being sent, back to headworks, miscellaneous plant use, or surface water or groundwater injection. The process flow diagram shown here depicts the process described on the previous slide with more specifications and detail. It displays the pump capacity and where all of the different effluent streams split off to their respective locations, such as surface or groundwater, and back into the system. It also depicts where in the process certain smaller portions occur, such as odor control and alum addition. Depicted here is the 5-stage biological nutrient removal system. Fermentation is where the activated sludge recycles into the process and is allowed to initially react with the influent to initiate the biological waste removal process. In the anoxic basins, there is a system deprived of oxygen so as to consume nitrogen from the wastewater influent. The aeration basins are where the process begins to need oxygen in order to reach its desired effluent process specifications. The first reaction occurs only in the anoxic basin. The denitrifying bacteria take the nitrates and turn them into nitrogen gas. This reaction is anaerobic and adds stress onto the bacteria as they are preferably aerobic heterotrophs. If oxygen is present, the bacteria will follow the second equation. Both reaction 2 and reaction 3 are done in the aeration basins. The second reaction is based around aerobic heterotrophs. They consume the organic carbon from the biological oxygen demand, along with oxygen, nitrogen, and phosphorus. This mainly reduces the phosphorus in the water. The third reaction is autotrophic nitrifying bacteria. They consume ammonia and carbon dioxide in the water. They produce nitrates that will be consumed in the anoxic basins. This reaction requires long residence times to grow the nitrifying bacteria. The aerobic heterotrophs outcompete the nitrifying bacteria, though not listed in the reaction equations. All these reactions create more bacteria for the overall process. The other main units used throughout the wastewater treatment process are the secondary clarifiers, which is where the activated sludge from the 5-stage biological nutrient removal process is allowed to settle out in order to be removed from the clean water and recycled back into the fermentation basins. On average, about 60% of the activated sludge is returned to the process. Before this stage of the process, alum is added to the wastewater. This is to flocculate any remaining phosphorus so it will settle with the sludge. After the clarifiers, the chlorination and dechlorination of water is done in order to sanitize it further and to get it to the correct effluent requirements. In this unit, the water moves into a chamber and chlorine is released into it. And then it moves to the second part of the process where the chlorine is removed to a level that is no longer harmful to the environment. This is the biowind model we created in order to model the process and observe the effects of different variables on the process effluent, power consumption, and its ability to handle the range of loads that can be presented to this plant. The process starts with the influent going into grit tanks, then the 5-stage biological nutrient removal portion. Alum is added to reduce phosphate before the clarifiers. The top portion of the clarifiers goes through a dewatering unit before being pumped as the effluent out into the surface water and/or groundwater. The bottoms of the clarifiers allow the sludge to settle and is pumped to be recycled or wasted as defined by the split ratio. The red arrows represent waste and the green arrows represent recycled streams. Here you can see the different specifications for size and power requirement that were used in the biowind model units. Here you can also see the different types of each major unit based on where they were purchased and the process requirements. The assumptions that we made in modeling this process are that there are no headworks included because it cannot properly be modeled in biowind. There are no chlorine contact chambers because they cannot properly be modeled in biowind. Filters are replaced by dewatering units because of the data that is available. Multiple pumps are combined into one pump with a power representing the sum of the individual pumps. It is assumed that the influent profile is constant day to day, and for costing purposes, it is assumed that the plant life is 10 to 12 years. As well as, with the exception of the aeration basins, it is assumed that power to each unit is constant. The volume of the influent to the plant is tracked over a 24-hour period and shows here in the graph, as expected, the volume goes up throughout the day and then stays steady through the evening hours. This is a picture of the pipe that carries the influent into the plant. These are the influent characteristics that were used in our model of the plant. These were taken as the maximum expected concentrations for the plant. These values allow us to evaluate the plant when it is under stress and achieve the values that are necessary in order to meet the requirements set forth by the EPA and the local government. To set up this biowind model, the influent concentrations are put into an influent specifier model off of the Valrico plant to give the appropriate wastewater fractions related to our data. The solid retention time for the sludge is set to 28 days. This means that after 28 days, the sludge is dumped and newer sludge is allowed to accumulate and run through the system. For the units, all the parameters such as kinetic, aeration, and diffusion, and the temperature are turned on, and the temperatures are set at 25 degrees Celsius. Here you can see the concentrations of the different contaminants that are tracked throughout the system, coming out of the process prior to our optimization. These are the best results that could be achieved in our model of the plant under our current settings. This graph shows the total suspended solids in our model based on current plant specifications. According to our model, the plant is not retaining enough of the suspended solids to reduce the nitrogen and phosphorus to acceptable concentrations. The plant uses 60% recycle of suspended solids at the current time. The suspended solids are important since they represent the bacteria needed for the chemical reactions within the 5-stage biological process. The suspended solids should be between 2,600 and 3,600 milligrams per liter. The concentration should not exceed the plant capacity, which is 4,000 milligrams per liter.
Equipment costs were determined from a cost report from the Northwest plant. The report includes data about the original costs of the equipment, along with the life of the equipment, installation year, last inspection date, and the replacement cost. When determining the numbers associated with the two major units, the replacement cost was used in the calculations if the piece of equipment was past its service life. Originally, anoxic basins and aeration basins were going to be costed out separately, but due to the design in the plant, they have to be combined into one value, as they share the same structure and some of the equipment. Energy optimization is imperative for any plant, as it is often one of the highest expenses of the plant. Prior to optimization, these are the energy requirements for the respective units of the process. As you can see from this chart, aeration basins and sludge recycle pumping consume a majority of the energy used by the plant. Thus, the scheduling and appropriate control of the requirements for aeration and pumping of the process sludge recycle are necessary for reducing the cost and environmental impact of the plant itself. The minimum cost of electricity for the Northwest plant is $200,000 per month. Scheduling equipment to run at lower power during peak hours and full power during off-peak hours can greatly reduce electricity costs. Peak hours are the time when more people are using electricity and therefore electricity is at higher demand. The table on the left shows the difference in energy costs during peak hours and off-peak hours. Peak hours and off-peak hours vary during different times of the year. In Florida, peak hours are 12 a.m. to 9 p.m. from April to October, and 6 a.m. to 10 a.m., then 6 p.m. to 10 p.m. from November to March. These times are based on tourism and other factors. This is why scheduling of the aeration and pumping is important for electricity cost minimization, as the time of day you use the power does change the cost of operation significantly. To start optimizing, a sensitivity analysis is done by adjusting different components of the model. In order to judge the effectiveness of the changes, the total nitrogen concentration was monitored. We chose to track the nitrogen because it is the hardest contaminant to manipulate. A decrease in the nitrogen concentration seemed to result in a decrease in all the other contaminant concentrations. The variable of interest include the power to the aeration basins and the recycle to waste sludge ratio. Using the base model with specifications provided in the plant, the aeration was increased to 500 horsepower and then decreased to 100 horsepower to determine the optimum power requirement. As seen in the graph, the best amount of power seemed to lie between 150 horsepower and 300 horsepower. These values were used when making a schedule for the aeration basins. Next, the recycle ratio of sludge was varied. The plant currently recycles only about 60% of their sludge, which hinders the denitrification process by not maintaining enough total suspended solids in their basins. The increase in recycle reflects this in the nitrogen concentration values. Therefore, in our model, we increase the recycle ratio to 90% to reduce the nitrogen in the effluent. By changing the recycle and aeration power, the effluent concentrations of all the contaminants were decreased. This graph shows the concentrations in the effluent after optimization. The peaks and dips in the concentration are due to the schedule created to reduce the utility costs. As seen here, the nitrogen concentration is the most impacted by the change in power. The aerator power at peak and off-peak hours was chosen such that the concentration of nitrogen stays below a concentration of 5 milligrams per liter. Prior to optimization, the concentration of nitrogen ranged between 6 milligrams per liter and 8 milligrams per liter. As stated previously, nitrogen is the most difficult concentration to reduce, therefore the focus was on keeping the nitrogen low. This graph shows the concentration of suspended solids after optimization for the aeration, reaeration, and anoxic basins. The optimized concentration is higher than the initial concentration when using plant specifications. However, it is still slightly below the 2600 to 3600 milligram per liter range that is typically expected. Since the range is a soft constraint and our nitrogen and phosphorus values are below the acceptable concentration, it was determined that the optimized concentration of suspended solids is appropriate for our model. Also, after optimization, the suspended solids concentration appears to remain much more constant than in the initial model. Further optimization could be done by adding a controller to maintain a higher level of suspended solids. The table seen here shows the results of the effluent after the simulation of the optimized model. We can verify that the optimization was adequate by comparing these values to the effluent requirements. The total nitrogen concentration should be below 3 milligrams per liter, total phosphates below 1 milligram per liter, total suspended solids below 5 milligrams per liter, and CBOD below 5 milligrams per liter. The pH should be between 6 and 8.5. Our results lie beneath these restrictions except for the total nitrogen. Since suspended solids exit in their own stream or are recycled back to the process, there should be no suspended solids in the effluent. Power for the aeration basins was put on a schedule to reduce the amount of power used. Scheduling is not based on influent flow rates but on electricity costs. The aeration basins require the most power to operate and have the most effect on effluent nitrogen concentration, which is why scheduling these units is more important than scheduling for other units. Power usage was reduced by half during on-peak hours of the day, since electricity costs are higher during these times. During off-peak hours, the aerators are run at full power since electricity costs are lower. By reducing power usage during peak hours, energy costs are reduced from $21,000 per month to about $9,000 per month. This cost estimate only includes the cost to run the basins and the pumps, not the cost of running the entire plant. This is why our cost estimate is much less than the actual plant electricity cost. The HAZOP analysis shown analyzes major components in the process and the possible consequences if something goes wrong. The return-activated sludge pump is key in keeping the 5-step biological process running. The sludge contains the cells that process the contaminants in the water. A reduced flow from the pump will cause issues with getting the contaminant concentrations down to the desired levels, possibly causing environmental and health issues if this water is to be released into the environment. There is also the potential to cause a backup in the clarifier line, which will reduce the efficiency of the unit. The alum pump regulates the phosphorus level entering the secondary clarifier. If not enough alum is added to the water before the clarifier, phosphorus can remain in the clarifier effluent and lead to problems in downstream units. High levels of oxygen will detrimentally affect the anoxic basin as the bacteria will revert to a more desirable reaction. This can lead to problems downstream involving the quantity of cells. Some of the cells die while in the anoxic basin. If the aerobic reaction is done instead of the anaerobic, there is no stress to kill the cells off. The larger volume of cells moving through the system will inundate the secondary clarifier. The lack of dissolved oxygen from the aerators will cause a similar scenario. A lack of oxygen will stress the cells and cause more cell deaths in the system. This will produce more foam on the surface of the water, requiring a longer residence time in the clarifier. Otherwise, it will cause later problems in other units. All of these issues can be protected against by sampling the water periodically to ensure the concentration levels are accurate. Adding a controller can help prevent these issues from occurring. The main concern in wastewater treatment is the concentration of CVODs, suspended solids, phosphate, and nitrogen in the effluent. If these values are too high, it can cause algae growth in bodies of water, killing off wildlife and damaging the ecosystem in the body of water where the contaminants are released, creating what is called a dead zone. This is why meeting EPA requirements for these values is very important. Another concern is the environmental impact created by power consumption. TECO uses coal and natural gas to make electricity. Burning these resources results in greenhouse gases such as CO2 and N2O. Acid rain, smog, and respiratory health issues are all associated with the accumulation of greenhouse gases in the atmosphere. Aside from cost, this is another reason for keeping utility usage as low as possible. In conclusion, the model and modifications done here are a successful representation of what could be done to improve the treatment process. This includes adding an aeration schedule based on peak TECO hours and changing the waste-activated sludge recycle ratio. Other modifications using this model can be further explored, such as adding controllers to adjust for different influent oxygen requirements, therefore more effectively controlling the aeration basins and saving on cost. Also, a controller can be added to increase the amount of sludge remaining in the basins in order to maximize conversion. Thus, this is an accurate and successful computer model representing the Northwest Advanced Wastewater Treatment Plant, We are the wastewater experts, and we thank you for your time. These are our references, and we'd like to thank Dr. Sanal and Kamal for their time and help on this project.